Okay, so we're going to talk about this thing called Vector Symbolic Architectures. And really this is meant just as the title says, really, an introduction, and hopefully quite a hands-on introduction. If you read some of the literature for this, it can be a bit jargon heavy, I would say, for something that maybe isn't quite as complex as it first seems. So hopefully this is a kind of like, if you wanted to build your own little hello world vector symbolic architecture, you might be able to at least have a crack at it after this talk. Okay, so what are we talking about? So roughly speaking, like very roughly speaking, right, in AI we split into these two kind of fields of study, right? We have symbolic computing, where we're representing concepts as symbols which are manipulated by rules. So we've got an example here of like some formal logic that we've written down, but of course this could be any programming language basically. If you've done any programming, which I'm guessing everyone here probably has at some point, you are basically dealing with symbols, and those symbols are being manipulated by some rules of some kind. Very easy to read through. Well, in theory it's easy to read through and understand what it is that the author of that code is doing. Connectionism is, again, the other sort of side of the fence, really, in the field of AI. And this is where concepts are represented as distributed patterns across networks of simple interacting units. Neural networks, I guess everyone's probably at least heard of neural networks, if not played around with them a little bit, fall into this field of connectionism. And obviously, if we look inside a neural network, you're not seeing a particular sort of part of that network which represents a concept. The ideas are spread in a distributed way across these nodes. Historically, connectionism was kind of coming from the idea that you should start by looking at the human mind itself, like the actual sort of mechanics of the mind, and sort of work your way from there. So the idea that if you look inside the brain, you're not seeing like a part of the brain that like that's the memory of this thing. It's spread across, right? There's not one sort of dedicated spot that's responsible for a particular memory. And whereas the symbolists were kind of coming from the more theoretical kind of logical point of view, saying, well, if we can just get the right algorithm, then we can develop something that's intelligent. Vector symbolic architectures, what we're going to talk about today, basically sit somewhere between these two worlds. So concepts are represented as symbolic structures, but they're encoded as these distributed vectors. So if we're going to try and develop what is an alternative computational framework to what we're used to. So the first thing we would have to think about is how we're going to represent data. So in traditional computing, right, we represent data as these precise, compact binary encodings. So this is the binary for, this is the number 5, right? It's just a representation that we've come up with, and that's how we sort of represent things in traditional computing. In our VSA, what we're going to do is we're going to represent our symbols or our concepts as these large random binary vectors. So here we've got this concept of Alice. It's just a symbol, just a token that we're calling Alice, and we're going to represent it literally. Obviously I've truncated it somewhat, but it's literally just a random list of zeros and ones that we've generated at runtime. So just a quick recap, what is a vector? Like a vector is literally just a list of numbers, right? If you represent it in Python or your favorite language, it's literally just an ordered list of numbers. That's all a vector is. But we interpret vectors to mean different things depending on the instance, of what we're talking about. We first really encounter vectors in physical, like geometric applications, right? So the coordinates on a map, for example. So we've got a two-dimensional vector, right? We've all seen this before. X, Y coordinates, latitude, longitude. It's just a list of numbers that we are interpreting as being a position in space on a map. 3 dimensions, again, it's a position in 3-dimensional space. Just think of a drone or something flying around. When we talk about vectors for more abstract cases, which is what we're going to do today, we often refer back to the geometric interpretation because it gives us an intuition of what it is we're talking about. We talk about them being points in space, we talk about the distances between them, even though they're not really points in space because we're interpreting them to mean something very different. So when we said that Alice is a point in 10,000 dimensional vector, obviously we can't visualize 10,000 dimensions. We can't really visualize 4 dimensions, right? Because we don't live in a world where that's an intuitive thing. But for all extent and purposes, we can just think of it as a point in space still. So Alice is still just this point in space. Just think of it like a star that's floating in space. It just happens to be 10,000 dimensional space, which we can talk about shortly. So we've got two tables, right? So we've got the table which is going to basically encode our concepts. So we've got Alice, and I've introduced some more symbols into the system. And this is just a lookup table, right? It just allows us to look up the vectors. These are different random vectors. Just imagine these were generated like when the system started up. And if I was to give you one of those vectors, you could decode it, because you could just have the opposite table, right? So the key and the value is swapped around. You could just say, what does this vector represent? Okay, it represents Alice, or it represents Bob, whatever that might be. Now, let me see what the next slide can be. So let's think about some of the properties of high-dimensional space. Well, one thing to say before we move on to that. If one of these vectors was corrupted in some way, so let's say I took the vector for Alice, and some of the bits were flipped, right? So we just accidentally corrupted it. You wouldn't be able to do the lookup exactly, but you could find the nearest match, right? You'd just basically say, okay, well, it probably was Alice because it matches in, let's say 9,000 of the dimensions, but it's corrupted in some of the other ones. So you could still recover the original vector. So some of the properties of high-dimensional space. So one thing to think about is that the probability of two concepts having identical vectors is very small, to say the least, right? There's no way that you're going to accidentally pick two vectors that have identical sequences of zeros and ones, right? That's like two people tossing exactly the same sequence of coin tosses 10,000 times in a row, right? It's to all extent purposes impossible. What's more is that randomly assigned vectors are almost always different to each other, meaning they're not even going to be close to each other in this high-dimensional space, right? They're not even going to be close to being actually identical to each other, or even close to each other. What this means is that high-dimensional random vectors are highly redundant, so each piece of that vector is just as important or just as pointless as every other bit. As I mentioned previously, if we were to corrupt that vector, it actually wouldn't really be a problem, because you could still go and recover the original vector. So to think about that in terms of the geometric interpretation, the idea is that Alice is a point in space, and the corrupted version of Alice is Alice plus noise. It's still going to be in the same neighborhood as that vector. You can recover it in the geometric interpretation. You can just measure the shortest distance between this and the seed vector, right? So you can just take what we call the Euclidean distance, just take using Pythagoras to find out, but you can use cosine similarity, or you can just look at the bits and say, well, that one's clearly going to match. Because the space is so sparse, so sparsity is the term which talks about, right? The idea that there's so much space in this space because it's very unlikely you're going to get a clash. It means there's no chance that Alice plus noise is going to wander into a different neighborhood. It's not going to start looking closer to age or Z, or at least it has to be corrupted a significant amount for that to happen. So this is just a property of very high-dimensional space. If you had two-dimensional space, like a dartboard, and you were throwing darts at the dartboard, then for a clash to happen, just two things have to happen, right? Two coincidences, the X and the Y have to match. If you have two drones flying around a field, then three things have to match, right? You have three coincidences, X, Y, and Z. As we keep adding dimensions, more and more coincidences have to happen. To the point when you get to 10,000 dimensions, that's never going to happen, right? So this is what we mean by sparsity. Space becomes sparser the more dimensions that you have. This is called cleanup memory in the literature, and this will become critical to how these things operate shortly. Okay, so we can represent our seed vectors, but what we want to be able to do now is link concepts together, right? So in traditional programming, right, variable assignment is probably the most common one. We might want to have three, Alice knows Bob, or we might want to assign a property to one of the concepts. Basically, you have two tokens, and you just want them to be connected in some way. So we need to be able to do this in our VSA in order for us to be able to encode that kind of system. So the way that we're going to do that is by actually combining the two vectors using an exclusive OR operation, which is going to produce a single vector that represents their association. So I think everyone might be familiar with this, but if you're not, you take the seed vector for name, you take the seed vector for Alice, and then you just compare the columns, right? So an exclusive OR just means if exactly one of the inputs is 1, then the output is 1. Otherwise, it's a 0. So you can see here, the first one is 0 because there's two 1s, the second one's 1 because there's 1, and so forth. What this has done is it's giving us a new 10,000 dimensional vector, a new point in this space, which literally represents these two symbols being bound together. So if our system was just name equals Alice, it's just a vector. We're always trying to get to a single vector that represents the system. If I gave you that binding, you could query it, you could unpick it by essentially just doing the exclusive OR again. So if I handed you the vector, which is name Alice, and you wanted to know what is the name, you would take the vector for name, and you would just do the exclusive OR. Exclusive OR has this really nice property that it just undoes itself, right? If you exclusive OR something with itself, it disappears. If you think about that for a few seconds, you can think why that happens. So if you exclusive OR something that is the composite of those two vectors, then it just disappears. This is like using cryptography. This is like the fundamentals of cryptography, basically, how private keys work. So we can unpick it. What's really remarkable about this is that if name and Alice is corrupted, so if I gave you the vector which is Alice and name, and it's again corrupted, you could still do this. What you get is Alice plus noise out the other end, and you could use the cleanup memory approach, whichever you choose, Euclidean distance or cosine, to retrieve the what it was actually meant to be. That's what this slide tells us, right? So these bindings are still resilient to noise, and we can recover that concept even from a corrupted one. So hopefully that's clear. What's happening is noise is just noise, right? So when you exclusive OR it with the random vector name, it's just more noise. So you just have Alice plus noise, and our system can deal with noise because of the sparsity of the space. Okay, the next thing we want to be able to do is group our bindings, right? So we do groupings all the time in programming, right? We have a dictionary, we might have an object, we might have a structure, whatever it is. It can represent maybe a person, it could represent a graph, it could represent all sorts of things. But if we want to model things in code, then we need to be able to do this kind of grouping of our bindings. So we're going to look at how we might do that now. So the first step is you take the things that you want to group, and you do the bindings as we did them before. So on the left here, we're taking name. This circle with a cross through it is the shorthand for exclusive OR. So we're just doing that exclusive ORs again. And then we're going to stack them on top of each other. So we're stacking the bindings on top of each other. And we're creating this thing called a superposition. And there's a number of different ways in the literature that you can do this, this superposition. That's basically squashing of these vectors into a single vector. But this one is doing the majority vote. So it's just looking at each column and saying, like, okay, there's more ones than there are zeros, so it's 1. Or if there are more zeros, then it's 0. So we've just squashed this thing into a single vector. Again, it's a high-dimensional, point in high-dimensional space, which represents this object, Alice. Now this is a lossy operation, right? We can't just unpick this operation. This isn't like the exclusive OR where you can just undo it. Because obviously there's any number of vectors that would map to that superposition, so we can't just perfectly unpick it. However, it turns out, let's check this next slide. Yes, so before we talk about unpicking it, there's something we should think about. So this vector now represents this object as a single point. And actually what we can do is we can compare those vectors directly. So if you had one of these vectors which represents Alice, and like Alice's occupation and age, and you have to say another one which is like Bob, then objects with similar properties would sit closer together in that space, right? You'd have this natural clustering that would happen. So all the Alices in the database, the vector store, would sit close to each other. All the vets would sit close to each other. All the people who are 42 would sit close to each other. Remember, in 10,000 dimensions, there's lots of different ways you can sit close to each other, right? It's not just a two-dimensional thing that we're thinking about. So we already have this kind of, sanity might not be the word, but there's a structure there which is giving us the ability to compare what would be similar objects to one another through these high-dimensional vectors. As we said a minute ago, the superposition is lossy, so you can't uniquely reverse it, but you can still query the vector. So if I gave you the vector that represents Alice, who's a vet, who's 42, this object, and you wanted to know what's the value bound to names, i.e. what's Alice, then what you can actually do is you can just do what you did before. You can just take the vector, which is the superposition representing Alice, and you can exclusive OR it with name. And what you will get back is Alice plus noise. So So the reason that that works is because if you think about what superposition is, it's these bindings that have been squashed together. And when you exclusive orbit, name disappears somehow, the signal of name disappears, and you're left with Alice still. Plus, obviously, all the other stuff, like the occupation, the age, and everything else. But that was also hit by the vector name, which is a random vector. And if you hit something with a random vector, which wasn't composed with that random vector in the first place, it just obliterates any information that's there, right? That's what private key encryption is. It just destroys it, essentially. So it just becomes noise. That makes sense, which is distributed across those 10,000 dimensions. And our system is very resilient to noise, right, for these 10,000 dimensions. So we can go back and we can do the cleanup step that we did before, and we can recover the original value. Cool. Let's move on. So the final thing we're going to do before we actually look at computation is ordering. So obviously we want to be able to order stuff in memory as well, right? So an array is the classic example, but we do ordering all over the place. So we need in our computational framework an ability to have some concept of order. So obviously the objects that we've looked at so far, the groupings, are just like a bag of concepts, right? There's no actual ordering there, no inherent ordering. So if we think about how ordering is done just normally in, let's say, C. In C, right, we represent order by physical position on disk, right? So 42, 17, 93. Imagine these numbers were stored on disk, and you have an array. And an array is just a pointer to the first position of the list, right? That's all an array is, right? It's just literally a pointer. And then when we access other elements in the array, what we do is we just add an offset to that start address. So when we see, my array 2, that's just shorthand for add 2 addresses to the current address. It just means get the 2 things to the right. If you think of it like houses on the street, the array is just the address of the first one, and this square bracket is how we sort of retrieve it. This is why we count from 0, right, in computing. We're saying don't add anything to the address, just give me the thing that's the address now. And that's the first thing in the address. Generally speaking, if we're stepping back for a second, the order here is emerging from the repeated application of an operation. We're just saying add 2 things, add 4 things, add 5 things. It's just an operation that we're applying, which happens to be addition in this case. And we can use that concept in our VSA. So what we do is we choose a random base vector, which is representing the list. So if we have a list called customers, for example, then we just pick a 10,000 dimensional vector, which is the list, customers. And if we want to put Alice in the first position of that list, then we just do the exclusive OR as we did it before. So we just literally bind it to the first position. If we want to put something in the second position, then we just apply a permutation to the base vector. So any operation, so in this case we're just rolling it, right? So just move every bit one to the right and the end one wraps round. If you roll a random vector, you've essentially just got another random vector. It's like sometimes called a pseudo-random vector, but to all extent it's a random vector. But it's a random vector we can derive from another random vector. If we want to put something in the third position, then we just roll it twice, right? So now we have another vector that we can get it back from the original one. So once we've done that binding, we can then squash them together using our superposition operation that we picked, which could be the Majorov-Souveau idea again. And now if you want to query the vector, you just do what you did before. You just take the customer array, you roll it however many times you need to in terms of find that position, and what you'll get back is the thing you're looking for plus noise, and you can use the cleanup memory step to recover the original C vector. Okay, I couldn't find a good graphic for this slide, so it's just blank space. So we can do binding, we can do grouping, we can do ordering of information, and as I sort of briefly mentioned, we can actually use these operations in connecting them together, right? We can have a list of objects that would then squash into a single point. So we can create very complex structured objects in high-dimensional space. As was mentioned, there is a capacity issue, which is constrained by dimensionality and also the cleanup mechanism that you're using. But ultimately, there is this compact, noise-tolerant way that we can actually represent and query these representations. We're going to move into computation next. But before I do, again, let's let's just pause in case anyone's got any thoughts or observations or questions of any kind. Cool, let's press on. So what we've talked about really up till now is just representation, right? How do we store things? We haven't done any computation. We haven't asked how would you actually manipulate this data and compute something. So just as a simple sort of way of demonstrating how you might go about doing something like computation, we're just going to look at a finite state machine. So very simple. This is like the hello world of finite state machines, and I guess everyone's probably come across this at some point. But you have these two states, right, which is the boxes, and this one is doing a thing called parity checking. So we've got some zeros and ones there, we've got two examples, and this machine is going to calculate whether there's an even number of ones or there's an odd number of ones in the string of zeros and ones. I realise there's a lot of zeros and ones going on in this talk, right? These are different zeros and ones to the ones that are repeated, right? This is just the thing that people like to do, or not like to do. It's something you need to do in engineering, right? You need to check the parity of the bits occasionally. So you just follow the arrows around as you process each bit. So you start in even and you just move around. I think everyone's hopefully familiar with this. And when you haven't got any more bits to process, then whatever state you're left in is the answer. That's what gets output as being the answer. And the idea is that the machine has computed something. It's counted. There's an even or there's an odd number of bits. So in order for us to do this in our VSA, what we're going to do is we're going to take this transition table, which obviously perfectly describes the diagram that we just saw previously, the current state, the input, the next state, and we're going to squash it into a single point vector, which represents our machine, our transition table. So we're going to do it as we did before. Now we're binding three things together. So these are even, we're going to create a random vector, which is the token even, another one which is the token odd, and then we're going to also have some for 0 and 1 for 1. And then we're just going to bind them, and then we're going to squash them. So we have a high dimensional point in space that represents the table. Then what we're going to do is basically have this machine that takes as input, so the 0 and 1. It's going to convert it to the seed vector. So in all practicality, what would happen is that 0 and 1 would be one hot encoded, and then matrix multiplied against the table, which is our lookup table, which is giving us, i.e. which of the seed vectors is 0 and 1. You just think of it as a lookup table. Then we're going to have a vector which is the initial state, which is even, which is going to have an exclusive OR. So remember, the pluses are exclusive OR. That's going to give us an output. We're going to exclusive OR that output. So we've now bound the current state with the current input symbol as a vector. And we're going to exclusive OR that with the transition table, which again, remember, is another 10,000 dimensional point. And that's going to give us the next state that we're transitioning to plus noise. That's going to go into the cleanup memory, and that's going to give us a new current state. And that's going to loop back around, and we're going to process the next bit in the input. So if you think about what's going on here, like so far, I guess we've probably been visualizing implementing this like in our favorite programming language. Let's say it's like Python that we've been thinking about doing this in. And obviously Python is a symbolic language that's running on traditional von Neumann architecture with silicon and everything else, right? But that's just a simulation, really, of something that actually is more abstract, right? You can imagine creating this machine just as being a series of exclusive ORs across arrays of 10,000 bits. Like, there's nothing in here there's no single point of failure. This is a distributed system of parallel computation. You could throw lots of noise at this, right? You could just be flipping bits all over the place, and it would have resilience. It's not like your symbolic one where it would fall over very quickly. This is a very robust way of doing computation. And you could just build some custom hardware for this if you wanted to. You could just make this out of anything that you possibly could think of that you wanted to actually implement it on. Now, if you're looking at that and thinking it looks quite a lot like a recursive neural network, it's because it kind of is a connectionist system, right? It's coming from exactly the world of how this stuff is, how people were thinking about this stuff. What's happened is that we've deliberately constructed this machine rather than a machine that's learned how to do something through the process of gradient descent or propagation. So just in fact to touch on this, one of the use cases for VSAs are very experimental things, as you can imagine, but one of the potential use cases is when you're looking at alternatives to silicon. So if you're looking to do something like nano computing or something, and you're looking at, say, like biological substrate to do your computation, then you have what is referred to often as stochastic hardware. So hardware which you can't rely on to be reliable because it just is so small or so unusual in its properties that it has a lot of noise in it. So if you have a system like this, then it can actually start to be something that you might be able to use. So, as we've just described, right, this would be a fully distributed computing system. No single bit or location would encode meaning or perform computation independently. And really what we're getting here, and this I guess is kind of when I sort of became quite interested in this, obviously computation really extends beyond traditional symbolic machines, right? We think about computation very much locked into our sort of programming world, but actually these distributed machines can absolutely do similar things. And this is of course not a new idea, right? This is a neural network that was set in the 1950s. And these patch cables, all these cables going out the back, these are all these connections between this neural network. This is obviously an example of a machine learning neural network. This was learning through the process of backpropagation, but there certainly wasn't, these machines were resilient to noise as well, right? There's anecdotal evidence that if parts were failing, it was still actually able to function because it didn't actually require everything in that network in order for it to work. I haven't got previews, is right? Yes, okay. So in modern neural networks, meaning in computation are distributed across many simple networks, units, sorry. The difference is that they are learning their own high-dimensional representations known as embeddings. So if you've ever looked at embeddings, you've probably been thinking through this, well, this sounds like embeddings, and what's happening with embeddings is either the network has directly learned embeddings, it's been trained to deliberately try and cluster or learn these representations that sort of clusters data in some way, or it's a side effect of some other task that it's trying to learn. It's trying to learn how to distinguish between dogs and cats, pictures of dogs and cats. So therefore, internally, it's found some distributed representation where dogs sit over here and the cats sit over here. You've got to get this natural clustering kind of information, this semantic encoding. And we see this all the time now with modern large language models. There are language models that produce embeddings for us. The idea that in like a RAG system, for example, the query is matched to the relevant part of the vector store based on this comparison of the two vectors because of the semantic encoding. But it's that encoding is being learned as opposed to constructed, even though you could, in theory, construct a representation of that text data using something like a VSA. But then we also have to think about the computation, and obviously we could go into some discussion about it, but in terms of what is it that these large language models have learned, well, network prediction is the reward signal perhaps is how they've been trained, but those transformers have learned ways of manipulating and changing the representations that it's learned in order to do complex computation. Again, we have to break out this idea that computation is just something that we can think of and program. There's obviously a vast universe of computable functions that we could never write ourselves, but that could be learned by a machine. So that's the end of the talk. It was, like I say, meant to, I wasn't sure on the timing of it, but it was, hopefully that's a good introduction. Any questions or thoughts?